Okay, so now we're going to start the last chapter, chapter 9, which is flow over immersed boundaries. We are definitely not going to cover all of this. Um, Courses in aerodynamics cover flow over immersed boundaries in much more detail than we will in this class. But flow over in immersed boundary means that you have the object is immersed in a moving fluid, experiences a resultant force due to interactions between the body and the surrounding fluid. This also works for a body moving in a stationary fluid. Okay, so the big thing here is just that you have some body, can look like that, and it just has to be immersed, totally immersed in the fluid. And so here we'll have some sort of streamlines going over the body like this, and the fluid has to be completely surrounding the object. Okay, and we'll assume that cap U is called the free stream velocity. And we will assume that U is steady and uniform. That means that if I draw a velocity rake here of U, that means that the velocity U is the same as it is here, as it is here, as it is here, as it is here, for all time. And this is far upstream or far in front of the object. Okay, and now as this flow moves, gets closer and closer to the object, it's going to experience the effect of the object, and the streamline is going to be turned up and go over and around, and then downstream of the object, or on the back side of it, the streamlines will eventually, after a long time, become steady and uniform again. Okay, and so the free stream is an upstream velocity, and this is the downstream side. Okay, and this is our object. And due to the fluid moving around the object, there is a net drag force on the object. There is always a drag force, and if the object or flow is asymmetric, there can be a left force. Okay. Now, and I'll show this in a classic video towards the end of the lectures for this chapter, is that even if the free stream velocity is steady, the flow near the object may be locally unsteady. Okay, and I will show a movie of this later on, and that is of something called a Kármán vortex street. And so here we have an object, and this has to do with the vortex shedding the oscillatory behavior behind a body. Okay, and you remember me drawing this before, where as a function of time you have this alternating series of counter rotating vortexes. Oops, and I drew this one backwards. Okay, and basically this streamline here, it basically sort of flaps around as a function of time, and because the flow is not symmetric on the back of this object or a cylinder, like sometimes there is a lift force going up, and sometimes there is a lift force going down, and that basically introduces a vibrating motion to the object. And towards the end of this chapter, I'll show another old classic video basically showing this phenomenon. If any of you have seen a stop sign shake from side to side in a torsional manner in a high-speed wind, it's actually this phenomena here is actually causing that. Okay? And so there are common types of bodies. Okay, there are two-dimensional objects, which are basically rods of some cross-section, and the flow usually goes over and around them. And the idea here is to study how the flow goes over and around an object in a two-dimensional manner. And the object is normally long enough such that the end effects, that is the fluid interacting with the portion of the object that has basically been cut off, is not important. Okay, and so this is 2D. Okay, there are axisymmetric, and so here you have some sort of body of revolution. A bullet would be an example of one. And then there are full-on 3D objects. So a model airplane would be one. And again, draw my really bad airplane. Okay. And so there are all kinds of flow characteristics that are associated with these different types of bodies. And needless to say, especially for 3D, the flow over an entire airplane can be extraordinarily complex. Okay. Oh, and I forgot to draw the free stream velocity u. Okay. Now, at the end of the day, the lifting, which if I scroll up again, I forgot to draw that. I forgot to draw that. There will be a drag force that will try to make this object move backwards, and there might be a lifting force that basically tries to make it move upwards, and I'll use a script L for that. Okay, and a sort of a scriptish D for the drag force. Okay, and so lift and drag are caused by pressure and viscous shear on the object, a surface. Okay, and so if you have some sort of a body here, I'll draw sort of an airfoil type thing. It looks something like that. Okay, and so on the surface of this object, you'll have pressure forces pushing down on it. Maybe it may be more back there, and you may have negative pressure actually pushing, acting in the reverse direction. That is very possible sometimes. And so here you have pressure forces that are pushing on the surface, and then you have viscous viscous shear forces that are acting tangential to the surface. Okay, And so to find the lift and drag forces, all you need to do, well, all in quotation marks, is you need to integrate P and tau over the surface. Okay, and I forgot to draw a tau. Okay, and so if we take a little hunk here and do a little blow up, basically near that, we have the surface of the object right here. And if I draw, oops, sorry, I keep bumping, X and Y, and I draw a line normal to the surface and define theta from the negative x-axis. So theta is defined differently than it normally is. Just be aware of that. And this is a small little patch. I'll call that area dA. And you'll have some pressure force that's pushing down on it. And so that's P. And that direction here would be theta. And you have some tau wall that is trying to drag up on it. Okay. And so if we consider the geometry here and the directions of the pressure and the wall shear stress, the drag force is the force that is acting along the x-axis, and I should actually draw U here. Okay, and so the drag force is acting along the x-axis. And the lift force is trying to pick up on that small panel. And so the drag equals the integral over the surface on the object times dfx. So basically, on each panel, we need to find the from the pressure and the viscous shear stress, we need to find the x component of those forces. So this would that would equal that would equal the surface integral over the object area of P times cosine theta plus the wall shear stress times sine theta. And that's over each patch dA. Okay? And this pressure term here is called pressure drag. And this term due to wall shear stress is called friction drag. Or skin friction. Okay, and so you'll see the term skin friction being used quite a bit. And again, this just involves the basic geometry and the angles and the direction of the pressure in the wall shear stress in this picture here. Okay, and then the lift force is just simply the y component. That equals the integral over the entire object surface. Object. dFy. And that equals, if we just consider the geometry again, the integral over the area times, well here, the lift is the y force, so we have actually pressure that's actually pushing down, so that's minus P sine theta, and we have the shear stress actually trying to pick up on the object, and so we have plus tau wall cosine theta dA. Okay, and so essentially then what the name of the game here is with the external flow is to actually find the pressure distribution and the shear stress distribution on the surface of our object, so we can actually perform these integrals and then find the net forces acting on them. Okay. And typically these are embroiled in terms of the drag and lift coefficients. So the drag coefficient, that's CD, and lift coefficient, that's CL. Okay, and the drag coefficient is defined as the drag force over 1/2 rho times the free stream velocity squared times A. And I'll define what A is later on, because it is different for different scenarios. You need to be careful of that if you look up drag coefficients in tables and things like that. You need to be very careful what how A is defined. And there's the lift coefficient, and that is similar to the drag coefficient, except for it's the lift force rather than the drag force. So it's the lift force divided by, oops, got to scroll the screen back out again, divided by the dynamic pressure, rho, that is 1/2 rho u squared, times the area. Okay, and this characteristic area here has many definitions. So you need to be careful. Okay. And so one of the more common ones that you'll see, it's called the frontal area. Okay, and that is the area seen that is, or let me do that again. That is the projected area seen by looking at object in the direction of flow. Okay, and you can think of this as the area of a shadow, the area of a shadow cast by light in the direction of fluid flow. Okay, and so you could imagine we have some sort of object here, and we have u going down into the left. Here, I don't know why I chose that, I just did. So our free stream velocity would be u going down into the left, and so we have an imaginary plane that we draw a normal to the flow, and then we just basically pick the outer edge of it and sort of imagine the shadow that actually would be cast. Okay, and so this would be the shadow. And the area of the shadow is the frontal area. Okay. And so, for example, say we have a sphere. For sphere, where we have just a circle and another circle in the crosswise direction, and we have u going in this direction here. Actually, for a sphere, it doesn't matter which direction I pick. So we have u, Well, we draw our plane normal, and the projected area is just a circle. Which has pi r squared would be the frontal area. Okay, and sometimes we will be using the planform area. Okay, and that's the area looking above. Okay, and this is useful for wings and flat plates. Okay, so say we have some goofy object here, and the flow is going in this direction. Okay, well, if we draw our projection normal to the velocity vector, this would be the planform area. Okay, and for the same object, the frontal area would be, again, you draw, you pick the opposite plane to project upon, and then that will give us the frontal area. Okay, and so for a lot of things, you can find the drag coefficient in lots of books and things like that. You just need to be careful as to how that area is defined. Sometimes, if you're unsure, it is almost always stated with the table, and so you just need to be very careful as to which area they are using. Okay, and so I'm gonna have a quick example. We have a pressure distribution on a cone. By rotating an equilateral triangle. Okay, so if we looked at a side view of the cone, it would look like an equilateral triangle where the height of every edge is 0.1 feet. Okay, and it's 60 degrees, 60 degrees, 60 degrees. So it's and then you just spin this around the x-axis. You spin this triangle around the x-axis, and you get this cone here. And the pressure distribution looks something like this. It is linearly dependent, and the peak value here is 1/2 rho u squared, so it's just the dynamic pressure. And on the rear surface, we have a negative pressure, so that's actually pulling backwards. Instead of pushing, it's pulling. And for many practical things, a significant portion of the drag on an object actually comes from subatmospheric pressure that forms behind the object. Okay, so some of the most intense pressure drag is not from the high pressure on the front of it. It's due to very low pressure, basically trying to suck it backwards. And so that is quite often the case. And so this pressure equals -1/4 rho u squared. So, oops, that should be cap u. Cap u squared. Okay, and so this height here is 0.1 feet. Okay, and this is a linear distribution. Okay, and the free stream velocity equals 5 feet per second. And that's going in the x direction. Okay, and so we are asked find CD and CL, neglect skin friction. Okay, and so the solution, well, CD, that's equal to the drag force acting on the object, divided by 1/2 rho u squared, and since we're not told anything, and for an object such as this cone, it is more traditional to use the frontal area, so we will define that using a frontal. Okay, and then the lift coefficient equals the lift force over 1/2 rho u squared a, and again that would again be the frontal area, but now the pressure distribution, because this is a cone and the pressure distribution we're assuming is axisymmetric, it's perfectly symmetric, so we have a symmetric force distribution in the y direction, so there are no lift forces. So symmetric forces on symmetric object. Okay, if for some reason we had a pressure distribution to where the pressure was higher on the bottom part of the cone, then there would be a net lift force either up or down. Okay, so just be careful of that. Okay, then in this case, to find the drag force, we just need to walk around the entire surface and integrate the pressure forces. Okay, and so drag, oops, wrong one, drag equals the integral over the object of the forces in the x direction, and that equals, well, we only have pressure, so that will equal to the integral over the front portion of it, that is the tip of the cone, and I'll just call this the x component of the pressure forces, dA, and I'll define that later, and oops, and this integral should not be closed, it's open, times the integral on the rear, the x component of the pressure forces times that differential area. Okay, and so we will work with first the front. Okay, so for the front, we have our cone. I'll draw a triangle here and bisect that. So this is the midplane. This would be 30 degrees. And to do the integral of the pressure on the front and the x component of that, we need to just consider the pressure. The pressure always acts normal to the surface. So this would be P. And this angle here, based on geometry, is 60 degrees. Okay, and so P, x equals the pressure at location x, and I'm defining x to be going, in this case, I'm defining x to be along the surface of the cone. So that is going up. I'm going to define that as y, or I mean as x, sorry about that. And so that equals some pressure as a function of x times cosine of 60 degrees. Okay, and now we're going to consider a small differential patch here. This patch would be a width dx, and this patch is actually a small ring. Okay, and so because the patch is a small ring, dA will equal to 2 pi r dx. Okay, and so this distance here is r. So we need to find r as a function of x. Okay, so I'll draw a similar triangle over here on the right. And so we have x would be this length here. This is our angle theta, and this is our height r. Okay, and so r, just based on the triangle, equals x sine theta. And that equals x sine of 30 degrees. Okay? So this equals 2 pi x sine 30 degrees dx. Okay? And then on the surface, we have a pressure, and it is linear, and we know that at the tip of the cone, the pressure is maximum at 1/2 rho u squared. It's a really bad rho. 1/2 rho u squared. And we have P. P0 equals 1/2 P0 equals 1/2 rho u squared, and this is the end of the cone at the top, and this is, I'll call this length L, and P of L equals 0. Okay, and so we have a linear, oops, wrong one, I had the eraser on by accident. So we have a linear distribution of pressure that looks something like that. And we know at x equals 0, the pressure is this value here. At x equals L, the pressure is this value here. So basically, you can fit a line to those 2 points, because in the instructions of the problem, so we know that Px are the pressure here as a function of x equals pressure at 0 times 1 minus x over L, where L equals 0.1 feet. Okay, and so now we just need to integrate this. So the drag contribution from the pointy part of the cone is equal to the integral over the entire length of this pressure times dA, which is 2 pi x sine 30 dx. Okay? So this equals 0 to the end of it, which is at 0.1 feet, times the pressure. So I'll just call this P0 times the linear distribution, 1 minus x over L, times the direction of the pressure force. So that's cosine 60. This whole thing here is what I called Px, times dA, which is 2 pi x sine 30 degrees dx. And this would be, oops, why did it make it trapezoid? This would be r. Okay. So I pull out everything that's constant. This equals 2 pi times P0 times cosine 60 degrees times sine 30 degrees times the integral from 0 to 0.1 x times 1 minus x over 0.1 feet dx. And if we stick in the numbers, this equals 0.001309 rho u squared equals d front. Okay, because that's P naught equals 1/2 rho u squared. Okay. And actually, this would have us, if I'm being really picky with the units, this would be feet squared. Okay. And then the drag on the rear, that equals the integral over the rear area, dfx. That equals, well, the pressure on the rear is constant. That equals integral over a rear, p at the rear, cosine of 180 degrees, dA. And the reason that the angle here is 180 degrees is, just remember that the surface is that this here is the rear surface of the cone. And remember that when we're computing drag, the pressure is acting in the x direction, but it's on the opposite face. So theta starts from the negative x-axis and goes to where the force is acting, or it goes to the normal direction to the surface. So this is theta equals 180 degrees. Okay, and so that would be y. Okay, and so p rear, this would be minus 1. P rear equals minus 1/4 rho u squared. And since that's constant, you can pull that out. And if you stick in the numbers, stick in the minus 1/4 times minus 1, you will get 0.0019 635 rho u squared, and that should be multiplied by feet squared. Okay, and then notice that in this case here, there is more drag from the rear than front. Okay, because just notice that that this drag value from the rear is higher than it is on the front. Okay, so CD equals the drag force over 1/2 rho u squared, a frontal squared. Well, this is a cone, so the frontal area is just a circle of pi over 4 d squared. Okay, and so we stick in the numbers that we computed. We have 0.001309 rho u squared feet squared from the front, plus 0.0019 635 rho u squared feet squared from the rear, divided by 1/2 rho u squared times pi over 4 times 0.1 feet squared. So notice that all the rho u squareds cancel out. The feet squareds will basically cancel out. And if you punch in the numbers, we are left with that the drag coefficient equals 0.8333, and the lift coefficient is equal to 0 because we had a symmetric force distribution acting on a symmetric object. Okay, so now that we've discussed the basics of the drag coefficient and the lift coefficient, we'll discuss some basic flow characteristics past objects. So characteristics of flow past an object. Okay, and so here we'll just consider some sort of 2D cylinder. And if the Reynolds number is very low, so RED equals rho times the free stream velocity times the diameter divided by the dynamic viscosity, or if you prefer, UD over nu, there are the same difference. If RED is less than 1, we have a scenario called creeping flow. And the streamlines for this case will look nice and symmetric, and they'll go nice over and around, and they'll be almost symmetric. Okay, and so for this case, the flow Reynolds number based on diameter is less than 1, and I'm going to highlight the region that is affected by viscosity, and that's, I'm going to use a thicker thing, and that is basically everywhere. So for a very low Reynolds number flow, that means the diameter here is big, and that means that the viscous forces on the denominator are dominating over the inertial forces at the top. This means that that viscous forces important everywhere. Okay. Now, if we bump the Reynolds number up to, say, RED around 50, we wind up with a different flow pattern around the object, is that the streamlines are not now nice and symmetric, and they don't just hug nicely around the object. In this case, what the streamlines look like is the front looks kind of the same, or qualitatively similar, but it goes over around, and it takes a lot longer to merge in the back. Okay, and what happens here is the flow actually separates, and you get what's called a separation bubble, which is a pair of counter-rotating vortexes that are attached to the rear surface of the cylinder. Okay, and this is called a separation bubble. Okay, and this point here, it's called a separation point. And we'll discuss a little bit more about those later on. Okay, and then in this region here, it turns out that the region where viscosity is important is not the entire flow domain like it was for the creeping flow with a very small Reynolds number. Instead, the region where viscous effects are important is actually confined to be somewhat close to the cylinder, and so then that is in this region here. Okay, and so this is where viscous effects are important. Now, if we bump the Reynolds number up to a very high number, say 10 to the 5th, which is considerably higher, we see a completely different flow pattern. So here we got the cylinder. Again, the front looks kind of the same, but the streamlines now are all jiggly in the back, and that's because this region behind the cylinder is actually turbulent, and we have separation points behind the cylinder, and the streamlines from the separation points are again all jiggly, and we have turbulence. Okay, and this region here that is affected, that is behind the cylinder and is sort of messed up by it, is called the wake region. And it's not unlike in the wake behind a boat or something like that. They're actually very similar. But now in this case, it turns out that the region where the viscosity is important is not far in front of the cylinder like it was for the smaller Reynolds numbers cases. Instead, it's confined to a very thin region near the surface of the cylinder and in the wake region. Okay, so I'm just going to highlight where viscous effects are important. That'd be in this region here. Then use the smaller one. Okay, and so again, the green area is where the viscous effects are important, and this thin little thing in front of the cylinder is called a boundary layer. Okay, and there's sort of a fun region where if the Reynolds number is between 60 and 5,000, the flow behind the cylinder actually oscillates. And I've sketched this a few times. And I've been promising a video, so I'm going to show it. Okay, and so in this case, there's an intermediate range of Reynolds number where the flow actually oscillates behind the object, and this can cause massive problems if you are not prepared for it. So I'm going to show you a quick video of that, an oldie but a goodie.
If a cylinder is not rotating, however, oscillation of the flow pattern will cause the circulation to vary first in one direction and then in the other, with the result that there is a rapid oscillation in the cross thrust. This explains the tendency for telephone wires to sing in a high wind, or it explains the whistling sound that is given off by this rod as it's swung rapidly through the air. Observation of the flow pattern behind such a cylinder will reveal the alternate shedding of vortices either side of the center line, the circulation around each vortex being just the opposite of the momentary circulation around the cylinder producing the side thrust. The succession of such vortices is called the Kármán vortex trail. If the cylinder is free to oscillate under the side thrust, as it is if suspended from light springs, it will gradually develop an oscillatory motion in the transverse direction and eventually move back and forth over a distance about equal to its diameter. An elliptical cylinder with major axis in the direction of the flow will have a more limited amplitude of oscillation, whereas one with its major axis normal to the flow will oscillate much more markedly. Some asymmetric forms, like either this semicircular cylinder or ice-encrusted telephone wires, are unstable in that they will tend to oscillate farther and farther, with eventual breakage of the suspension as a result. A similar sort of instability is found in various structural sections. In particular, the Tacoma Narrows Bridge, here seen oscillating in a high wind prior to ultimate failure.